Hi, I'm Harry Porter, the designer of the EveCore microcontroller. This video comes at the end of a series of videos in which I showed how to implement a microcontroller core in Verilog. If you are unfamiliar with the EveCore architecture, you can visit the website shown at the bottom of the screen to learn more about it. I'm going to wrap this series up by making some general comments in this video about the EveCore design. I'm going to discuss in general terms some of the decisions that anyone who's designing a computer architecture might want to think about pretty seriously. I'm also going to talk about some of the lessons that I've learned and list some of the things that I think I did right, and I'm also going to talk about some of the mistakes that I made. Okay, so let's get started. We can begin by asking, what's the most important question when designing a new computer architecture? And if you think it's this, then I would respectfully suggest that you are quite wrong, that there's something that's far more important, and that is to ask, why in the world are you designing a new computer architecture? And who exactly is your audience? There are a lot of computer architectures already out there, and are you just reinventing the wheel for your own pleasure? Well, that's okay. If you want to design a computer for your own use, then go for it. But if you want it to be used by other people, then you need to ask very carefully, is there a need for a new computer architecture, and who would your audience be? In my case, I think it's educational primarily. Maybe there's some hobbyists out there who want to play around with FPGAs, but primarily I'm targeting students. If you want to learn how to program in assembly language, then the EveCore might be a good place to start. A little bit more simple than learning x86, 64. Also, if you are interested in learning Verilog and to see the connection about how computer architectures are actually implemented in hardware, then I think the EveCore could serve a function in that sort of education. Personally, I like programming in assembly language, and I myself wanted something that was enjoyable to program that was at the microcontroller level. I also wanted to make a series of videos on how to implement a computer core in Verilog, and for that I needed a simple computer architecture. I feel that there's not a lot of good material out there on how to implement cores in Verilog, and so I feel that there might be a slot or a place for something like the EveCore. And so that's my target. I also wanted to explore some of the choices that you might make at the microcontroller architecture level. I kind of got started because my son was taking a university class that was showing him how to program microcontrollers, and they were working with some of the common microcontrollers that are out there. And in order to help him, I had to review some of the documentation for these microcontrollers, and it's pretty dense stuff. I was a computer science professor for many years, and assigning students to wade through some of the documentation on things like the 8051 or the AVR is maybe too much, I think. They're not getting the big picture. I wanted something that was more easy or more appropriate for a first-year university engineering student. I think another question to ask is, what kind of software are you going to be running on this microcontroller? I mean, if it's a hobbyist and it's your own project, then you don't really need to ask that. You can do whatever you want with it. But if you're in a corporate environment or you're hoping to make a product, then you need to ask, for example, do you intend to support the C programming language? And if so, you're going to need to add some instructions to support multiple data sizes and so on. Also, do you intend to support a Unix-like operating system? I mean, I think we can define a microcontroller as any architecture that is just incapable of supporting a multitasking operating system. And so you need to ask, where is your architecture going to fit into the larger environment? You might also want to ask, is efficiency important? Is reliability important? Are you designing an avionics system where reliability is key, Or are you designing something that's going to be devoted to some particular computational project or process, in which case you need to design the architecture to be efficient in that particular domain? Now let's get back to this question of the number and the size of the registers, which is clearly a very important question to ask early on. There are a number of different data sizes, and one question is whether you're going to focus on one particular size to the exclusion of others, or whether you're going to try to handle several sizes pretty much equally well. You might also ask whether you're going to have instructions to make it easy to convert between one size and another, with truncation, sign extension, and so on. As for the number of registers, there's a spectrum from essentially one register to a bunch of registers. With a small number of registers, they tend to be more special purpose. It does result in shorter instruction opcodes, but on the other hand, the code sequences tend to involve more instructions, and this may make it a bit more difficult for the compiler to find good instruction sequences. If you have a bunch of registers, then it's more likely that they're going to be more general purpose. Of course, you'll have larger opcodes, and of course, more hardware resources will be consumed if you have a bunch of large registers than if you have a small number of small registers. Now let's take a look at the ALU instructions and the variety of formats and operand combinations you might want to support. On the top, we see the only option available in the EveCore, and working down we see some other variations you might want to include. With EveCore instructions, the operands must come from the A and B registers, and the A and B registers become special purpose registers devoted to the ALU. They are no longer general purpose registers. However, you might want to allow one or even both operands to come from an arbitrary register, as shown here and here. Also, with the EveCore, the result is placed into one of the operands, and it seems to me that overwriting one of the operands with the result, as many architectures do, doesn't impose too great a burden for most code sequences. But you might want to include the ability to place the result in yet a third register, which we see right here. There's also the question of whether you want to allow one of the operands to be an immediate value in the instruction, and you might want to allow one of the operands to come from memory, which I haven't shown here. With the EveCore, if you want to use an immediate value, then you have to resort to an instruction sequence that involves an extra instruction. This may lengthen the code sequence by a little bit, but not too much. If you want to use general purpose registers or other registers for ALU operations, with EveCore we end up with code sequences like this, which we tend to see a lot of. And obviously, if you have only a single simple format like the EveCore, you can get by with smaller opcodes, but the more different formats you add, the larger the opcodes are going to become. Now let's take a look at encoding, say, this sort of instruction right here into bits. And of course, every operand is going to require a field to specify the register, and you've also got a field for the function code. And you have to ask how many bits to allocate to the function code. And you can see pretty soon you're going to run out of bits, even with 2-byte opcodes, especially if you want to have more than 16 operations, for example, including various multiply and divide and rotate operations. We can also ask some questions about shifting and rotation. Do we shift by just one bit or an arbitrary number of bits? And does that value come from an immediate field, or is it found in one of the registers? Shifting and rotating don't seem to be very common, but they are necessary for encryption and computing secure hashes, and possibly some other algorithms as well. With EveCore, I just had the simplest approach with a shift by a single bit, with the assumption that if you wanted to do more complex shifts and rotates, you could write some code that would do that. One very important consideration to think about is the length of instructions. With RISC-V and ARM, we have fixed size instructions, while with x86 and microcontrollers we have variable-sized instructions. The fact that RISC-V and ARM have both added compressed instruction formats over time clearly testifies, I think, to the importance of reducing code size. I mean, we can ask, where does execution speed come from? If we have simple instructions, then we can have faster pipeline stages and therefore run with higher clock rates. We've also got the question of decoding complex instruction formats. But I think really the key that we need to focus on is reducing code size. If we can efficiently encode our instructions, the programs will be smaller. And this is really important for two main reasons. Fetching the instructions from main memory is the first reason. That's truly a bottleneck and requires a lot of time. And a second sort of related effect is that with a given instruction cache of a fixed size, with more efficient encoding, we can get more instructions into the same cache and thereby reduce the pressure on fetching data from main memory. So I think the efficient encoding of instructions needs to have greater emphasis, and it's something that I want to work on with my Blitz64 architecture. This is a more complex architecture similar to RISC-V, and I think variable size instructions are a good idea. However, there are some very serious alignment issues. If you have a requirement that instructions and or data has to be aligned on particular boundaries, it's going to complicate the architecture if we allow variable-sized instructions. In particular, it might be with unaligned data and instructions. Items can cross cache lines, and this can be a huge problem in multi-core systems where you have multiple caches, and you might have the same piece of data cached partially in one cache and partially in another. So synchronization becomes something that you've got to be very careful about and think very clearly about. Of course, with EveCore, there are no alignment requirements. Everything is byte-oriented, so this issue just doesn't arise in the EveCore architecture. One thing that interests me is the relationship between the core architecture and an operating system kernel. In my Blitz64 project, I'm trying some different approaches to see what seems to work best from the point of view of a kernel writer. The instruction set architecture can be thought of as an interface between software and hardware. It's basically a border or a boundary that both programmers and circuit designers must respect. They can't cross it. I think we've become too locked in to an existing boundary, and of course that boundary is represented by the C language. Every new core architecture must support C. That's simply non-negotiable. Likewise, every kernel hacker just assumes that every modern core is going to support the C language, and it's completely inconceivable that there is actually any alternative. Chip design and kernel programming have become so specialized that moving that boundary around is completely unthinkable, at least at this point in time. With my Blitz64 project, I'm experimenting with the unthinkable and playing around with fire, I guess, to see exactly where we end up. Anyway, what do we need in any architecture to support something like a Unix-based kernel? Certainly, we need interrupts. Not just for the timer alone, in order to implement time slicing, but also to handle I/O peripheral devices. The timer is core specific, while, at least in a multi-core system, dealing with peripherals is really quite a different problem. Also, we need some ability to save registers when an interrupt occurs so that we can return to the interrupted code at some point in the future. We want the interrupted code to continue execution as if nothing has happened. For example, the EveCore has condition code bits, a program counter, and a stack pointer in addition to the registers, and these all need to be saved. The EveCore has, in fact, no way to access the status register, the program counter and the stack pointer as data values. We're also going to need some control registers for any use in interrupt handler code. These are needed to maintain context so that the kernel can take over after an interrupt. To support a kernel, we also need modes. Basically, the kernel needs to operate in a different mode and different privileges than the user mode code executes in. We also need different classes of instructions. Basically, we need privileged instructions for the kernel, that is for code that's executing in kernel mode, and we need unprivileged instructions which can be executed by both kernel code and user level code. We also need a syscall instruction, which is going to be used to transition from user code to kernel code, and that would be used to implement system calls. And to support multiple processes and to protect them from each other, the usual solution is virtual address spaces, and these are implemented with page tables and translation look-aside buffers. So we're going to need that. And we're also going to need some way to protect the I/O peripheral devices from arbitrary user-level code. Well, while none of this stuff is present in the EveCore, I do want to say that it's all present in the Blitz64 system that I'm working on. Every program needs the ability to compare two values and conditionally execute some instructions and not other instructions. In designing EveCore, I looked at two separate approaches shown here. There are some other approaches, such as conditional execution, which are very good, but I don't think they're really appropriate for something like EveCore that's a microcontroller. In the first approach, you have two instructions. The first one does the comparison, and then it sets some condition code flag somewhere, and the second instruction tests those flags and then does the conditional branch. In the other approach, you combine it into one instruction, and so you don't need any other condition code flags. And that can be especially useful if you have interrupts, so you don't have any condition code flags to save. So I thought very seriously about that. With EveCore, you only have one way to compare operands. They have to be in registers A and B, so there's only one compare instruction. It would be useful to have some other comparison instructions. For example, we might like to compare against 0 or an arbitrary register or an immediate value, or even compare two registers. And these could be added as other instructions. If you had taken the second approach, well, we have a bunch of different conditional branch instructions, and if you multiply that by all the different operand combinations, you get a lot of different instructions. So with this approach, you can have a bunch of different compare instructions followed by a bunch of different conditional test instructions. So with the EveCore, we have the 0, the sign, and the carry flags, which I think are just about the minimum of any microcontroller. We also have an overflow flag, which is needed for sign comparison, so I went with just these 4. Some microcontrollers also have a half carry flag, and they use that for binary coded decimal operations. And I don't know, I just don't think that doing arithmetic computation on binary coded decimal is a particularly good idea. If you're going to do anything, just create a decimal add instruction that works on BCD and a decimal subtract instruction that works on BCD. Or maybe skip those altogether and do everything in binary and just have two instructions to convert from binary to BCD and BCD to binary. Computers oftentimes have a program status word. That is, they group the condition codes and some other important bits into a single program status word. And in particular, there are usually some bits that control the interrupts and maybe the execution mode and some other stuff. And then you need a way to save and restore that program status word as a whole for interrupts. With the EveCore, we've gotten rid of all the other bits, and so maybe we could think about getting rid of the compare instruction and combining it with the branch instruction so that you wouldn't need any kind of way to save or restore the program status word on an interrupt. But of course, the EveCore has no interrupts, so that's not really a problem for us. Now let's talk about big endian versus little endian. This is a question of how multi-byte quantities are stored in memory. In my view, the issue is whether we store multi-byte quantities in the obvious, correct order, or whether we, for some reason, reverse the order, which is stupid. I mean, I've seen many students really confused by little endian order, and it's just prone to mistakes. Big endian seems correct and clear and straightforward. I mean, I understand how it evolved. I was writing assembly language programs back when, in order to add a multi-byte quantity, you had to index through memory and you had to fetch 1 byte and do the addition. And of course, you had to add the least significant bytes first, so it kind of made sense. But is there anybody that is still supporting little endian? I mean, is it just a legacy stupidity that we're hanging on to? Or is there some legitimate reason for it that I'm missing? Big endian seems very much the right way to do things, and I spent about a microsecond deciding that the EveCore was going to be a big endian computer. There are two approaches to memory: the von Neumann approach with a single unified memory, and the Harvard architecture with separate memories for program and data. One cool thing about microprocessors today is that the chips include a flash memory to hold the programs. This avoids all issues relating to booting and is perfect for embedded systems. So I started with a Harvard architecture, but at one point in the project I realized that the EveCore architecture would work equally well with a single unified memory, and this was really quite satisfying. The only instruction that was tied to the flash memory, that's the load code instruction, works just fine when both the program and the data are in the same address space. However, I will say that I designed the EveCore with the intent to model a typical microcontroller with flash, which is to be preloaded with the program code. Frankly, the EveCore is a little underspecified, shall we say, with regard to bootstrap loading in a von Neumann unified memory situation. Concerning addressing modes, microcontrollers typically use a variety of schemes to specify addresses. In addition to simple absolute addresses, some support PC relative addressing, and some have special regions, such as 0 pages, that have special addressing modes. Relative addresses have two benefits. First, they make code relocatable, and second, small offsets lead to shorter instructions and therefore more compact code. Code relocation is primarily useful for hackers who are writing viruses, and that's not exactly something we strive to support. In the early days, that is, before virtual addressing and page tables were invented, relocation was absolutely critical for the early operating systems. Today, I would suggest that there's really almost no need to write relocatable code, especially with the embedded systems. Alright, that said, I created a little boot program for the EveCore, which I called MiniBoot, which begins by relocating itself into high memory. The boot code begins by moving itself into high memory so that it can load the target program, which is non-relocatable, into address 0, where it expects to be. This was possible in the EveCore architecture, although the resulting code is not exactly the cleanest code. Well, in any case, relative addressing is clearly a great idea since it shortens instruction lengths, and well, in my opinion, it's worthy of careful tuning in future ISAs. 0 pages are special memory regions that have their own special addressing modes. These were necessary when memories were tiny and expensive and when every bit counted. This is not the world we live in today. 0 pages and some of the other funky addressing modes merely add headaches and complexity to a microcontroller architecture. So with EveCore, I went with the simplest addressing mode. Every address is a full 16-bit absolute address, period. beginning assembly programmers, frankly, have enough to struggle with. I'm not trying to save memory. I think 64 kilobytes is more than enough for any program that I can ever foresee running on an EveCore. 64 kilobytes gives you plenty of room to hold all the 16-bit addresses you're ever going to need. I was simply not trying to achieve maximal code density, at least not with the EveCore. Full-sized, absolute addresses seem ideal for the EveCore. Actually, I think this is an aspect that's critical for making the EveCore appropriate for students and beginning assembly programmers. Modern microcontrollers have mechanisms to protect the flash, typically using fuses. First of all, these add complexity, which clearly I wanted to avoid. Second, EveCore is primarily targeted at FPGAs, so there's not likely to be either flash or the ability to implement fuses. In some microcontrollers, the goal seems to avoid or hinder or prevent intellectual property theft. Another goal seems to be to prevent unauthorized applications or accidental modifications of the code. These objectives simply don't apply to the EveCore. If at some point you want to use the EveCore as the basis for silicon implementation with flash and possibly with fuses, which, by the way, I think would be an excellent student project, then you're going to need to augment the architecture. So I guess that addition to the EveCore specification will actually become a part of the project. I will just mention that the protection and security are in general critical issues for many application areas, and there are many approaches used in operating systems, but all of these were simply left out of the EveCore design. Maybe at this point I can put in a plug for my Blitz64 architecture, which employs modern mechanisms designed to support secure booting, preclude operating system corruption, and keep user mode code from misbehaving. But let's get back to the EveCore. Now let's talk about register mapping, which is done in some microcontrollers. The idea is that registers are stored directly in memory. In other words, there are some predefined addresses that are set aside to hold these registers. These special memory locations are really one and the same as the registers themselves. With this approach, the data in a register can be accessed, that is, queried or modified, by using instructions that load or store directly into memory. You can go directly to the memory location that holds the register and modify the memory, thereby modifying the register. And likewise, a few of these special memory locations can be modified by instructions that otherwise operate directly on registers. In modern architectures, registers and memory are very separate things, but with this register mapping going on, these older microcontrollers tend to blur the distinction. From a pedagogical point of view, I think it's important to keep registers and memories separate, at least for beginning assembly programmers who might be struggling with some of the very basic concepts. So what are the benefits of mapping registers to memory? In some cases, we may be able to avoid including some rarely used instructions that would operate directly on data in registers and just require the programmer to use similar memory-based instructions, which we were going to have to be including anyway. And this might reduce the number of instructions in the architecture. Also, there's a distinction between memory that is on-chip and memory that is off-chip. Since on-chip memory and register memory might be equally efficient in some situations, one question you could ask is, why do we need registers at all? Well, registers are probably more efficient than memory. In the EveCore design, for example, registers are accessed combinationally in the same cycle, while memory requires a full clock cycle. So there's that. I'm not going to argue for or against registers, although that's an interesting question. I'm just saying that in the days when some of the microcontrollers were designed, things might have been quite different. Anyway, I think that mapping complicates things, and I can't see really a good motivation for it. There's another thing to consider. Most processors usually have a number of special control and status registers, and these can be memory mapped. These perhaps they cannot be accessed using the normal register mode addressing, and that happens particularly since they're not general purpose registers. So somehow we need a way to access these special registers. For example, we might need to copy the program status word to memory during a context switch or interrupt. So one approach is to map these control and status registers to memory locations. That makes them easily accessible without having to add any special instructions, which is basically the other approach. It seems like a lot of effort to map registers into memory. In the EveCore, we don't really have any special registers that require direct access, except, of course, the I/O peripheral registers. And for these, we have dedicated operations, namely the in and the out instructions. I want to say a few more words about the registers that are associated with I/O peripheral devices. There are two common approaches. In the first, the registers are mapped into main memory locations, and in the second approach, there is a special address space for these registers. In the first approach, which you see in systems that are supporting operating system kernels, it might be that the memory protection mechanisms that are used to keep user processes separated from each other can be used to protect the registers associated with the devices. So whatever protection mechanisms the system is providing can just be extended to the I/O peripheral devices. This is the approach that I took in the Blitz64 system. The other approach, which is often used with microcontrollers and is used for the EveCore, is to map the registers associated with I/O peripherals into some kind of a special address space. In the case of EveCore, there's a space of 256 bytes. Now protection becomes somewhat of an issue if you want to provide protection, but it's not usually a problem for microcontrollers because there's no notion of protecting one process from another process. And it's also, I think, a bit easier to implement and maybe easier to understand. I also want to say a few things about bit operations. In the EveCore architecture, we can only shift by a single bit. We can shift left and right with and without carry, but we cannot shift by a variable number of bits. So the first instruction is part of the EveCore architecture, but the second and third instructions shown here are not. I mean, you can implement them, and in fact, it would be a good exercise to add instructions like the second instruction here or the third instruction to the architecture. Now, what happens if you want to actually do this? Well, there's a workaround for the second instruction. If you want to shift by, say, 4 bits, then you just need to code 4 shift instructions, one after the other. And if you want to shift by a number of bits that's computed at compile time, then you need to code a loop with a single bit shift as the loop body. Also, there is no rotate instruction in the EveCore architecture. Of course, again, you might want to add rotate instructions, either to rotate by a single bit or a variable number of bits. That's up to you. As for rotation, there are workarounds. You have to write a little code to do it. For example, to rotate a value in A left by a single bit, you could shift it left, shifting a bit into the carry. And if you shifted a 1 into the carry, then what you do is just set the least significant bit with this instruction, and otherwise you have shifted a 0 into the least significant end, and if you shifted the 0 out, then you go to skip here and don't do anything. So there are workarounds for what is available in the EveCore, and I thought it would be best to keep it simple as well as provide appropriate exercises for you to do by adding these instructions or writing the code to work around the instructions that are missing. Many microcontrollers contain instructions for manipulating individual bits within a byte. For example, they have instructions to set a particular bit within a byte, or clear a bit, or to test a particular bit within a byte. I chose not to include these bit manipulation instructions in the EveCore architecture, but of course you could add instructions like this if you wanted to. There are perfectly good workarounds. For example, to set a bit, you need to have an OR instruction. So we have to use an appropriate constant like this. You could express this constant either this way or this way. Both these two instructions would assemble to the exact same code. And to clear a bit, you're going to use an AND instruction with a similar constant that could be expressed either this way or this way. And finally, to test a bit, basically use an AND operation with a conditional jump after that. Forcing the programmer to use these workarounds might actually be healthy and good for them, to force them to understand bit manipulations and binary. I would ask whether these bit manipulation instructions are really needed that much. As time goes on, things are changing. In the early days of computers, bits were manipulated a lot more, it seems to me. And today we're manipulating larger quantities like bytes or 64-bit words or floating point values and so on. So I think there's less of a need for down and dirty bit manipulation, and I chose to leave these instructions out of the architecture. I also chose to leave out of EveCore any instructions that explicitly set or clear the condition code flags. Many microcontroller programs use the condition codes to indicate error indications on return from functions and to transmit information in other ways. If you want to program in that style, you're free to with the EveCore, and most likely you would use the 0 flag. You can use this instruction to set this particular condition code flag, and if you want to clear it, the workaround is to use these two instructions. The EveCore architecture does include a direct call instruction in which the absolute 16-bit address of the function you're going to call is included directly in the instruction. But the EveCore doesn't include an indirect call instruction where the address you're going to jump to is computed dynamically. Now you'd need an indirect call instruction if you're going to implement object-oriented programming on the architecture. And in particular, whenever you invoke a method and you're doing dynamic dispatching, you have to look up the target address in some kind of a jump table. And so you need an indirect call to make the method invocation. But basically, EveCore is just not really suited for advanced stuff like object-oriented programming. So I saw no reason to include this instruction in the architecture. There are a number of other features that are missing from the EveCore architecture. We have the add 16 operation, but you could ask whether there should be more 16-bit operations or maybe more 16-bit registers. One thing I wrestled with was whether the add 16 instruction should or should not modify the condition code flags. I decided not to modify the condition code flags, but I think a good argument could be made for the opposite approach. Another thing that is missing is any kind of conditional execution. We have the conditional branch instruction, of course, but some architectures have an ability to do something like what is shown here. There's some sort of a special flag, possibly in the program status word, and there are some instructions to set this flag. For example, you might set it if the less than condition is met and clear it otherwise, and then based on the setting of this flag, you may or may not execute several instructions. And this sort of thing is very important for execution speed, but I think it complicates the architecture quite a bit and the instruction encoding, and I felt it was just too complex for something like the EveCore architecture, so I left conditional execution out. Here are some other features that I've chosen to leave out of the EveCore that are included in most other microcontrollers. There is no sleep mode or power saving mode, and this is important in applications that are being powered by a battery where you need to do everything possible to reduce power consumption. There is no watchdog timer. The idea with the watchdog timer is that it's guarding against failures of some sort, and if the timer ever goes off, the system will automatically reset and start over. There's no brownout detection, which can be important for systems that are running on batteries and need to take action when the battery gets low. There are no timers or counters, and these could be very useful for pulse width modulated devices. So I thought about adding something like that so that we can drive a pulse width modulated servo motor or something with the EveCore. There is no particular support for debugging, and there is no specification in the architecture for how flash is to be loaded, and that is pretty much mandatory for any microcontroller that is powered by a flash or that includes a flash. All of these things could be added, but I think these are, more complex and would be needed for a real chip, but for the purposes of the EveCore, they are things that I think would be just too complex and not necessary to have. Now I want to talk about some of the mistakes I made and some of the things that I wish I had done differently. Currently, the encoding of the move instruction starts with 0, 1, but it should have been 0, 0. If it had been 0, 0, then a move from A into A, which is effectively a no-op, would have been encoded as a byte of all zeros, and this would have eliminated the need for a no-op instruction altogether, which I think would have been much cleaner. Another thing is for the assembly code, I am using uppercase for the registers, and I think it would be better to allow both lowercase and uppercase at the programmer's discretion. Also, the assembler directive .flash should have been something different. I chose .flash when I was thinking of the EveCore as just running on a Harvard architecture, but once I realized that it could run on a von Neumann unified memory, the .flash directive was not quite right, and I think .program would have been better. I thought about eliminating the load stack pointer instruction because it is going to be initialized to 0 on power up, and that will put the stack in upper memory in all cases. But it turns out that I did actually need the load stack pointer instruction in that mini boot program I wrote, so I guess I shouldn't eliminate the load SP instruction. Also, I didn't include a compare immediate instruction, and I think this would be a very useful instruction to have, and it wouldn't add much complexity at all. Also, the load M and store M instruction should also have accommodated the XY register. Those end up being good exercises for the interested student, I suppose. So I didn't go back and change those. Maybe also adding a mul step instruction, which is doing one step of the multiply iteration. Multiply is an important operation, and it's needed by a lot of programs, and so being able to do it quickly seems important. So I don't know, maybe adding that would have been a good idea too. One thing I realized is I really need to finish everything before making the videos. Once I made the videos, and I realized I needed to make some changes or wanted to make some changes, I really was stuck. I couldn't go back, for example, and redo the encoding for the instructions because I had already talked about that and in all the documentation. So in the future projects, I want to finish everything and make sure it's absolutely perfect before I even start making the videos. There are a number of decisions that I made for the EveCore architecture that I think turned out particularly well, and I wanted to mention a few of those. First of all, all addresses are absolute 16-bit values, and I think that turned out quite well. Second, I think the big Indian decision is correct and the only reasonable decision, so obviously I'm happy with that. Next, the strange and weird assembly language format that I'm using is somewhat experimental, but I was really quite pleased with that. I think that was really a nice way to do things. I was focusing on making the assembly code very readable, and I think that's very important for students and beginners. And I tried to make it look as much like C as possible, but still be a true assembly language. Also, the distinction between the load and the loadm instructions, and likewise the store and storeim instructions, turned out particularly well. With the load instruction, any register can be loaded, but the address is always an absolute value. Whereas with the loadm instruction, only the A register can be loaded, but we do an addition. With the loadm instruction, we add two things, and the immediate value could be an offset with m pointing to some kind of a structure, or it might be that the immediate value is the address of an array and m is an index into that array, or it could be that the immediate value is 0 and m is simply a pointer. But by keeping everything 16 bits, I didn't need to really distinguish between offsets and indexes and actual addresses, so everything works here. And also, if you just want a straight pointer, the immediate value would be 0, and of course, it wastes 2 bytes, but nowadays that's really not a problem at all. Also, I was kind of pleased with an architecture that I designed for a Harvard implementation. Turned out to really work just fine on the von Neumann implementation. So I was kind of pleased with that aspect of things. Also, I have only 3 instruction formats. The opcode is either followed by nothing, or an immediate 8-bit value, or an immediate 16-bit value. So the formats are very clear and simple, and I think that turned out particularly well. Also, I left out any bit-based operations to, set individual bits or clear or test individual bits within a byte, and I think that's a good decision. And we have a flat memory, okay, no special regions. There's no interrupt mechanism, and that makes things quite a bit simpler, and I think I'm happy with the simplicity that it affords. Also, many microcontrollers have an implicit increment or decrement when they do memory operations, and I left that out. It means separate instructions, and maybe things won't run as fast, but this thing is running, really fast on an FPGA, so execution speed is not really a problem that I'm too worried about, nor is code size a problem. So I think the simplicity that all of these provide is really a great thing with the EveCore architecture. EveCore is a one-person design. I got started when my son asked me for some help with his microcontroller class. I ended up going back to read and reread some of the material for the common microcontrollers that people are using today. I kept thinking how unnecessarily complicated and confusing these chips are. From there, a worm crawled into my brain, and I couldn't stop thinking, yuck, this stuff is awful. Why did they do this or that? Isn't there a better approach? Now, obviously, I have the experience of asking these questions in the year 2024. While these chips certainly could be improved with what we know today, let's remember they were designed a very, very long time ago. And these designs have proven themselves, they were successful, and today they're widely deployed. But I started playing around with some of the design ideas and asking myself, what would I do? If it were up to me, how exactly would I design a microcontroller architecture? I'd recently downloaded a cool little app for my iPad, something called Colanote, which my son was using to take notes in college. And I was having some fun playing around with it on a vacation. So basically, I sketched the entire EveCore design while sitting on the lanai looking out at the Pacific Ocean. I also invented my novel assembly language approach at the time, which I think is actually a pretty useful contribution worthy of wider consideration. In terms of realizing my design, I went home and started writing the ISA specification document so that I had something beyond my handwritten notes to work from. Dream designs in sand are basically just castles in the air. They're just a bunch of loose ideas floating around in your head. Our fantasies usually lack any clear definition or rigor, and they move around sort of like clouds. Our ideas really don't require any self-consistency, and often we can hold two complementary, competing ideas at the same time without even realizing that we're doing that. So you've got to begin with a clear, precise definition as the first step in moving beyond the world of crazy ideas. So next I started working on the Verilog code, and I also wrote the assembler, which was pretty quick, since I took a much more capable assembler I had and mostly just removed code from it. After I was about 95% done with the implementation and the written documentation, I started in on the videos, which took way more time than I expected, and more time than writing and coding combined. So there's some major benefits to designing and implementing everything yourself. That is, by a single person and not by a team or a committee, especially if you're not on a timeline or a tight schedule. But first, you can make major changes. You can add or modify anything you want. And since you're the same person making the design changes, who is also responsible for all the implementation of those changes, and who is responsible for all the documentation changes, you can accurately apprise and consider the implications of making any particular design change. Think about what would have to happen if you wanted to modify the behavior of one of the instructions in the x86 architecture. Forget about it. Design decisions made way back in the 1970s are, today, 50 years later, for better or worse, absolutely set in stone. Some of these design decisions were made before we have the knowledge that we have today. I'm thinking of Little Indian and some of the zero-page stuff myself. But certainly some of the decisions made years ago should be subject to questioning today. Some of these should, at least in my opinion, be changed or fixed. While they may have been excellent, smart trade-offs made at the time, we know way more now. We have more experience. We even have some wisdom. And since we now can cram like a jillion transistors on a single chip, the trade-off math has completely changed since then. Of course I realize that pretty much all the useful or complex projects will require big teams and decisions that are made by committees. No single person is ever going to design and build a complete airliner. And the same is basically true of modern chips. Nevertheless, there's a lot of value in small projects like the EveCore. First, you can achieve a simplicity and an elegance that's simply not possible with large projects. Second, a small project can explore the design space, and corporations and committees simply can't do this. They don't have the courage or the ability. So you can be creative and you can innovate with a small project. Finally, small projects like the EveCore have, I think, an important role to play in education. Imagine that you're a teacher of microcontrollers. Would it be easily doable to use EveCore to teach architecture, assembly language programming, and Verilog core design in a single semester? Okay, well, with all that, I think it's probably time to wrap up. Let me say that I hope you've learned something from these videos and from studying the EveCore. So what's next? Well, frankly, I'd like to implement the EveCore in Silicon. But to be honest, I don't have the skill to do this. If you have this skill and it's a project you're interested in, I would definitely like to hear from you. I mean, in general, I welcome your comments. If you have some remarks about these videos or about the EveCore design, I welcome your feedback. Send me an email. So I guess I'll end by saying thanks for studying the EveCore. Thanks for watching my videos, and happy programming.